Hello everyone, welcome back to another episode of Solving LeetCode Hard Question. Today's question is sliding window median. The question is as follows. You're given an integer array nums and an integer k. There is a sliding window of size k which is moving from the very left of the array to the very right. You can only see the k numbers in the window. Each time the sliding window moves right by one position. Return the median array for each window in the original array. For example, if nums is 1, 3, -1, -3, 5, 3, 6, 7, and k equals to 3. Starting from the first three elements, we have 1, 3, -1, and the median is 1. Moving right by one position, the new median becomes -1. And we repeat the same procedure until we get all the medians in the array. How do we solve this problem? Pause here if you like to think independently for a moment. First, let's think of the brute force approach. We can just sort every window and calculate the median respectively. Note that when k is an even number, the median is the average of the two middle elements. In other words, window at index k divided by 2 minus 1 and window at index k divided by 2. Add them up and divide the total by 2. If k is an odd number, then the median is just the middle element. The complexity of sorting an array is k log k, and we do that for every window starting from left to right, moving one position at a time. So the overall complexity is O of nk log k. Here is the pseudocode in Python. As mentioned, we get the subarray, sort them, and get the median for each of them as we slide through the window. Now the question is, how do we do better? Instead of sorting the array from scratch every time, we can make use of the fact that the previous window is already sorted and use that to construct our new window. Here's what I mean. Consider the same example 1, 3, -1, -3, 5, and k equals to 3. Our first sorted window is -1, 1, and 3. And as we move by one position to the right, we need to insert the new element -3 and remove the left element 1. And because the original window was already sorted, we can do our insertion and removal in a binary fashion, which allows us to achieve logarithmic time. In Python, we can use the library bisect for this. Here's the modify code. We start by sorting the first window and getting the median of it. Then, as we move the window at each step, we use binary search to insert the new element, and similarly to remove the old element, and we can get the median of the new window. The time complexity reduces to O of n log k because removal and insertion now takes log k time. And the space complexity is O of n because the size of the median array is n minus k. Can we do even better than that? Here are some hints. Instead of using a list, can we design a data structure to fit the goal of getting the median more easily? And if we choose our data structure carefully, do we have to remove the left elements as we move to the right, or can we save some cycles there? If we think about it, to get the median, we really just care about the middle element or middle two elements of the array. We don't care about the rest. So we can use two heaps, one max heap and one min heap to keep track of these two elements. Essentially, we would divide the window into two halves. In the first half, every element is smaller than the top element, denoted as L. And in the second half, every element is greater than the top element, denoted as H. So the median calculation is as follows. It's equal to L if k is odd, and it's L plus H divided by 2 if k is even. Now let's focus on how to adjust these two heaps as we slide to the right. So the goal here is to insert nums I plus k into the heaps and potentially removing nums I from the heaps. There are two cases. In case 1, nums I plus k and nums I are on the same side. This means that we would be adding an element and removing an element from the same side, and this doesn't change the median, as the left and right are still balanced, so there's no adjustment needed. However, in the second case, nums I plus k and nums I are on different sides. This means that we would be adding an element on one side and removing an element from the other side, so the two sections now become imbalanced, and we need to move the median 1 over. In this case, we need to pop an element from L to H. And since they're both at the top of the heap, such operation is all of one time. Let's elaborate a little bit more on when we actually have to remove the O element. First, we need to know which element corresponds to the old ones. So we need to keep track of the indices of inserted elements. Second, let's say the O element is somewhere in the heap. To remove it, we actually have to keep popping until it gets to the top of the heap, then add everything back in, which might take a lot of work. But as we've seen in previous slides, all we care about to calculate the median is the top of each heap. So the old element can stay inside the heap for as long as possible unless they get to the top. Then, because it affects the median calculation, we need to remove them. Otherwise, we can delay our cleanup. Putting everything together, here's the Python code. First, we initialize a max heap low and a min heap high. We would append both the value and the index to the heap. Then, at each step, we insert the element. If it belongs to the right, we insert it to the right. Otherwise, we insert it to the left. And if the element to be popped is on the opposite side, we need to perform a rebalance of the two heaps. In addition, if the top of the heap is an old element, we need to remove it so it doesn't affect our median calculation. At the end of the step, we can calculate the median by looking at the top of the two heaps. The final time complexity is O of n log k, which is the same as approach 2, although it's slightly faster because of the lazy removal optimization. And the space complexity is O of n. That's it for today. Let me know if you have any questions, and see you next time.